Students. So welcome everyone. This is Computer Science Talk session number 23 of the 7th Polygen Symposium of Rising Scholars. My name is Daphne. I'm going to be moderating today's session. The goal of this session and symposium in general is to celebrate and showcase the work of all of our Polygen students who have tirelessly worked on their project over the past couple of months with all of their mentors. We have 4 students presenting today within this talk session on a variety of topics. A fellow member of the Polygen team also might be scoring the students' presentations that will help us determine prize winners at the end, and y'all will get more information about those scores later on. We're going to have all the presenters present back to back 4 in a row, and then at the end I'll open up the floor for any Q&A. If you have any questions as the presenters share their information, feel free to go ahead and add it into the Q&A, and I'll make sure that I bring those up when we get to that section. So today's speakers are Varish, Siddharth, Arjun, and Ankhita, and we're going to go ahead and start with Varish. So if you want to go ahead and share your screen, and if everyone else will turn their cameras off, we'll get started.
Okay, almost.
And whenever you're ready, go ahead.
Yeah, almost. Okay, cool. Hello, everyone. My name is Varish Venkatesh, and today I'm going to be presenting my project, which is about using artificial intelligence to treat hydrocephalus. My mentor is a PhD Tia Rickens. Okay, so the first question is, what is hydrocephalus? Hydrocephalus is defined as the excess buildup of cerebrospinal fluid in brain ventricles. This can cause dementia, messes with the patient's brain growth, hinders motor coordination, and lowers the patient's bladder control. An average adult should have about 90 to 200 milliliters of cerebrospinal fluid in the brain. Any amount that is not in this range is considered as hydrocephalus. This disease has a very low survival rate, with 50% of the patients survive past infancy, and only 20% make it to adulthood. In the diagram on the right, we can see a patient with no hydrocephalus and with hydrocephalus. When a patient has no hydrocephalus, their brain ventricles are not inflamed. And we can see that it touches the brain, which causes the disease. Here we can see the brain ventricles build up pressure and inflame, which is what causes the dementia, hinders the growth, and motor coordination. Now, let's look at the history of hydrocephalus. Hydrocephalus goes all the way back till 1890, where the treatments first started. They used manual drainage with needles, which caused a lot of infections. This was improved by Nicholas Sen in 1903, created the first surgery using a perforated rubber tube, which is again improved in 1917, but William Sharp used line threads for his surgery, which reduced infections. So out of the 48 patients, only 28 survived and benefited from the surgery, which of course is not a great number, but it was an improvement. Arne Torkelson created the first usable catheter in 1940, which was then improved upon by Robert Bundes. Robert Bundes performed the first modern-day shunt surgery in 1957, which featured a silicone tip and a pressurized mechanical valve. Our design today is based on this invention. Now let's look at the present-day solution. The present-day solution works by having a pressurized shunt, which is attached from the brain ventricles to the abdomen, where the excess cerebrospinal fluid is transferred. A programmable shunt, which is used as a magnet, is used by physicians who can manually adjust the outtake and the intake rate of the cerebrospinal fluid. A shunt is inserted from the brain surgically and can take anywhere from 30 to 60 minutes to complete the surgical process. A patient must stay in the hospital for at least 24 hours until the CSF has stabilized. Now, if we look at the diagram on the right, we can see on the left, there is a person who, without the shunt, who has hydrocephalus, where they have a buildup of pressure in their brain ventricles. On the right, after going through shunt surgery, the shunt alleviates some of the pressure by taking all the cerebrospinal fluid from the brain ventricles and transferring to the abdomen, where it can be naturally processed. But there's a lot of problems with the current procedure. The first thing is that there's a risk of draining too much or too little cerebrospinal fluid. About 10% of patients experience this and can potentially cause seizures, brain clotting, which essentially makes the problem worse. Blockages are also caused when too much cerebrospinal fluid needs to exit at the same time. This needs further surgery to fix this and cannot be fixed by programmable shunts that are used today. Infections are also a major issue. Infections near the brain can potentially cause, which are potentially caused by frequent surgeries, can be fatal, especially since the brain is a really sensitive organ. And not only that, this is a huge cost issue, with the average surgery costing upwards of $35,000 and the need for multiple surgeries to maintain the shunt. The modern shunt is not accessible for a majority of patients. And that's when my solution comes in, Project ASH. My project that I dubbed ASH, known as Artificial Intelligence Shunt to Treat Hydrocephalus, is aimed to alleviate the problems of modern-day shunt surgery through the use of machine learning. My project focuses around artificial neural networks, which is a form of machine learning inspired by neural networks in humans' brains. Utilizing artificial neural networks will allow my shunt to learn and adapt to the patient's brain to keep the cerebrospinal fluid volumes in check, without risking factors such as over and under drainage. My project will be able to solve all the problems that revolve around the current day shunt surgery, and it will prevent the risk of blockage by using data that is gathered from the artificial neural networks to evenly intake the correct amount of cerebrospinal fluid in a steady rate. Right here is a model of my design, but it doesn't, and this is my full 3D print, but this doesn't look too good on the outside. The main interesting part is in the inside, as we can see here. This is all the internals of my device. And let's learn more about that in the next slide. So first, we can see that there's a silicone rubber tube that is used to transfer the cerebrospinal fluid from the brain to the main component and back to the abdomen. Next, we have the flow rate sensor, which is able to detect the flow rate of the cerebrospinal fluid, and this is the input data that my Arduino receives. This is what's used as the X value in the artificial neural network. Next, we have the main body, which is used to house all the components. Next, we have the breadboard, which is connected to the Arduino, which is then connected to all the sensors, so it can take all the output and input data and transfer it back into the Arduino. Then we have the Arduino microcontroller, which is in charge of getting all the input and output values and computing it through the form of artificial neural networks. Then we have the battery pack, which is used to power all these components. When this design is finalized, this battery pack will be able to wirelessly charge, so it does not have to be surgically removed every time you need to change the battery. Here is a upwards view of my device, and we can see this is the main pump that is used to transfer the cerebrospinal fluid accurately in precise amounts, so that you can so that there's no over and under drainage, which is the problem that is caused, as I mentioned earlier. But the question is, what is artificial neural networks? Here's a general diagram showing how artificial neural networks work. In this case, the X values, or the inputs, would be the values that are extracted from the pressurized sensor, or the flow sensor. Each of these values are assigned to a certain amount of time that the pressurized pump shunt will extract the cerebrospinal fluid. Each layer of code will take the values from the previous layer and multiply them by their designated weight until they reach the output values. Through the process of training, the accuracy of these values will increase. My Arduino will compute these values through my code. And here's my code. Instead of showing all my code line by line, I'm going to highlight some of the important aspects of it. So on the slide you see right here, we can see my output nodes and my input nodes. These values are not trained because my data is not complete. My trained values are not yet completely accurate. But here are the default values which I'm going to train. On the left, we can see the output values, and the right, we can see the input values. The input values in the diagram which I showed right here correlate to X, and the output would be the Y. Now here we can see some of the layers of how the weights are multiplied. This is my code for multiplying the weights for each layer, and we also need to detect any errors to make sure that the cerebrospinal fluid maintains the 90 to 200 milliliter mark. And this is my code to make sure that my data removes all values that might seem like an error. Now let's look at the setup for testing. There will be two chambers. One is the container with water with high amounts of sodium to replicate the cerebrospinal fluid. The other container is empty, representing the abdomen. The end of the tube with the silicone catheter goes to the sodium container. After this, I will change the volume of the container to the amount that is outside the 90 to 200 milliliters range. This means that the patient has hydrocephalus, and my device should be able to take the value that's outside the 90 to 200 milliliter range and make it so that it is inside the 90 to 200 milliliters range, essentially curing the patient of hydrocephalus temporarily. My project is still in the experimental phase. The success rate is not high enough to draw valid data points, but through more training and testing, my project will surely succeed. So now let's look at the future of my project. My invention of the artificial intelligence shunt will my invention of the artificial intelligence shunt may solve many problems with the current day shunt surgery. It reduces the need for regular checkups and reduces the overall cost, and it prevents the risk of over/under drainage, which is the main problem with the current day shunt. This invention can potentially increase the quality of life of many patients. Thank you for listening.
Thank you, Varish. So the next presenter is going to be Siddharth. If you want to go ahead and share your screen.
Yes, 1 second. Okay. Is my screen visible?
Yep. Whenever you're ready, go ahead.
So hello, my name is Siddharth Chander, and I'm a junior attending the Doherty Valley High School in San Ramon, California. And this is a presentation related to my paper, The Emergence of Quantum Advantage and Predictions Related to its Limiting Factors. And this paper covers topics included quantum computing, mathematics, physics, and computer science. Moving on to the purpose of the paper. We are currently at the threshold of quantum advantage. We finally have enough usable quantum bits to perform calculations that are too complex for classical devices to simulate in a reasonable time frame. This advantage over classical computers is only part of the motivation to pursue quantum computing. It has helped bolster quantum computing and is one of the recent interests in quantum hardware and algorithms, all to solve problems that haven't been solved by classical devices. Funding for quantum computing has increased and more than doubled since 2020, and the rate of funding in this field is increasing. Countries like China, Europe, and the US continue to invest billions of dollars in developing their quantum industries, and moreover, it has been predicted that quantum computing will be most useful in life sciences like molecule modeling and finance, as in portfolio optimization. So this slide contains an abstract of my paper housing similar information to what I previously told you. Please take a few seconds to read this abstract before we continue on the presentation. Now we'll begin with the basics of quantum computing. Quantum bits or qubits are the building blocks of quantum computers. They can store 0, 1, or a combination of 0 and 1. The state of a qubit can be a combination of 0 and 1, but when measured, the qubit will collapse into only one of two states. The ability for qubits to be in a combination of 0 and 1 states allows them to store additional information compared to classical bits. Qubits can be physically represented as superconducting circuits, trapped ions, and photonic or light-based circuits. Another important concept, quantum measurement, is when a quantum system is manipulated to determine its output state. Once a qubit is in the system and is measured, they'll collapse into one of two basis or basic states on a measurement basis, which are along the x, y, and z axis. Think of an x, y, and z axis on a three-dimensional plane. Qubit states are visualized using the block sphere, as seen on the next slide. Qubits are modeled as rays coming from the sphere center to the surface, between the endpoints of one of the three axes. Qubits can also be represented using ket notation, which is displayed on the next slide. So here we can see the block sphere and the ket notation, and ket notation can also be equated to actual vectors. Quantum gates. With an understanding of qubits, we can move on to quantum gates, which follow the same rules as classical gates by changing the state of input qubits based on a defined set of rules. Note that some quantum gates have no classical analog. There are a near infinite amount of quantum gates, and some important gates are shown on the next slide. Moving on to the next slide. After seeing some of the many types of quantum gates, you must consider the possibility of a set of universal quantum gates, or a set where any possible operation can be done on a quantum device using the gates on this slide and on other slides. There are many combinations, but the mention of universal quantum gates is enough for now. Now that we know the basics of quantum computers, we'll examine three unique properties that allow them to perform tasks differently from classical computers. In some cases, they complete tasks faster than classical computers. These three properties are quantum superposition, entanglement, and interference. Quantum superposition is when a qubit is in either one of two states or a combination/superposition of both states. The benefit of superposition is seen when using a quantum computer to try different paths in an algorithm. Think of a maze with different turns. When a qubit is in a superposition, quantum computers can simultaneously try two logical paths. Quantum superposition also allows for more information storage because if one qubit is in superposition, then the number of classical bits to represent this one qubit increases. This is because bits can only be in 0 and 1, but superposition states are represented with numbers besides 0 and 1, and multiple bits are needed for that. Essentially, superposition allows qubits to have exponentially more information than classical bits, but once a measurement happens, the qubit is reverted to a non-superposition or a classical state. Quantum entanglement is when two particles are connected across any distance. In this case, measuring one particle allows one to determine the second particle's state without another measurement. The primary benefit of entanglement is that information is stored in the system of entangled qubits rather than just in individual qubits. Essentially, entanglement is required for a quantum algorithm to achieve an exponential speedup compared to a classical algorithm, so superposition is not enough on its own. Quantum interference allows different states to affect each other. The primary use of interference is to allow a quantum computer to eliminate incorrect solutions without fully calculating them, as seen in different algorithms, including the one detailed on the slide, Grover's search algorithm. These unique properties allow quantum systems to theoretically solve new problems that are difficult or near impossible for classical systems to solve. Still, there are limitations for current classical quantum systems. One limitation is quantum decoherence or the loss of quantum coherence. When decoherence happens, quantum devices lose their quantum properties. So the development of long coherence and high fidelity qubits and gates have begun to provide results, aiding in reducing decoherence. Especially as more qubits are used for calculations, we need methods to correct these errors. So for example, decoherence. Concerning quantum advantage, quantum decoherence limits our ability to build systems with large number of qubits because we cannot perform calculations without errors. And this is one of the reasons quantum advantage has only been demonstrated in the past few years. Quantum errors are limitations for quantum computers, especially in their ability to run quantum algorithms. Quantum error correction works to fix errors in quantum gates, qubits, measurement, and the preparation of quantum systems for quantum usage. So turning on and setting up quantum computers for running quantum simulations and programs. A significant restriction to quantum error correction is the no-cloning theorem, which states that it's impossible to create an independent and identical copy of an unknown or unmeasured quantum state. In the end, quantum decoherence and errors are two causes limiting quantum hardware from reaching quantum advantage in more cases. Computational complexity useful in both classical and quantum computing measures the number of resources needed to run an algorithm. This notation in the form O of n is used to characterize algorithms based on their growth rate. With an understanding of computational complexity, we can move on to quantum advantage. Quantum advantage is when quantum computers outperform classical computers. In general, multiple factors allow quantum computers to achieve quantum advantage. And these factors are quantum superposition, entanglement, and interference. This topic is one of the primary focuses of my paper, and we'll move on to an important example of quantum advantage now. So the Hydrocephalus algorithm is the first example of demonstrating quantum advantage. So in essence, this algorithm aims to determine if f of x is a constant or balanced function by evaluating the function in the least amount of times possible compared to a classical computer. There is more to understand about this algorithm, but this is just the basics. There have been many recent events of quantum advantage, including in 2019, Google announcing that they achieved quantum advantage using a 54-qubit superconducting quantum computer. And Google performed calculations in 200 seconds compared to the 10,000 years needed to achieve the same result by a classical computer. Here are some more recent events about quantum advantage with an event from December 2020 and an event from June 2022 by different universities and different companies. Now we'll move on to the experiment I detailed in my paper, Google's 2019 claim to quantum advantage, which stemmed from random circuit sampling or the usage of randomly selected quantum circuits. Quantum interference aided in these situations. As the number of qubits and gates increased, it became exponentially harder for classical computers to simulate these circuits, primarily due to the extra amount of qubits and bits held in the circuits compared to what a classical computer can run. Essentially, Google used an algorithm that created a set of quantum circuits that were hard to run. So here's the future of quantum computing with quantum advantage. Quantum error correction methods will have to be developed for quantum computers to scale, as in compared to classical computers. And Google's primary goal is to achieve a fault-tolerant and error-free quantum computer for future applications like developing medicine and creating better materials. Now we'll look at some quantum hardware predictions I made. With the rise of quantum computers, their limitations are becoming more noticeable. To remedy this, quantum hardware is improved in two ways: the number of qubits and lower qubit error rates. And these are the two things I'll be discussing. So we can see that this is related to Google's 2019 demonstration of quantum advantage. The graph 2 slides ahead indicates an exponential growth of around 2.13 to the power of n, where n is the number of years since 2014, which is faster than the classical computing Moore's law, which is around 1.75 to the power of n. A quantum computer can be large enough to implement advanced quantum algorithms in the next few decades. So here's more information regarding my previous slide and my previous predictions. Here's the graph I was referring to. Now here are the quantum error rates I made. We also have data about the error rates of different quantum processors over multiple years. The minimum error rate is 1%, but not currently. There are devices with under 1%, but those devices don't work very well. So the equation of best fit from this data, which is shown again 2 slides ahead on another graph, is 5.06 to the power 2 times x to the power negative 0.64. So here's more information regarding the function that I previously mentioned and how it was used to make predictions. Here's the graph I was referring to previously. Ultimately, it is essential to note that we are currently at the threshold of quantum advantage. We now have enough usable qubits to perform calculations that are too computationally complex for any current classical device to simulate in a reasonable amount of time. I would like to end this presentation with a quote that hopefully shows you that quantum computing is a difficult concept to grasp, and there's still much to learn beyond this presentation. Thank you for listening to my presentation.
Thank you, Siddharth. Just as a reminder, in the interim between our last 2 presentations and our first, if anybody has any questions, feel free to throw them in the chat and we'll get to them at the end of all the presentations. Our next presenter will be Arjun.
All right. Can you see my screen properly?
Yes, you can go ahead whenever you're ready.
All right. Hi, everybody. My name is Arjun Kulkarni, and I'm going to be presenting my complexity theory research paper on the average case hardness of pattern matching in permutations. Okay. Hang on. All right. So I'm going to first go over like a lot of background. Computational complexity theory is like the subject of my paper, right? I'm like my paper falls under that subject, and it's analyzing the difficulty of computational or algorithmic problems. And okay, yeah. Time complexity, that's a very important part of complexity theory. And it's the time an algorithm takes to solve a problem, and it's dependent on input length. And I don't mean like 2 seconds, 4 seconds. I mean like, you know, how many roughly time steps as a function of like the input length. And I'll go over some examples maybe in like the future, or like, yeah, I guess just now. So an algorithm, polynomial time, an algorithm solves a problem in an amount of time steps, polynomial in input length. Okay, so for example, let's say there's a problem and let's say there's an input of size n, and you have an algorithm that solves in roughly quadratic amount of time steps. Okay, like quadratic in n, like n squared time steps. Okay, and that would be polynomial time. And you know, you can consider if the algorithm ran in like n cubed number of time steps, it's also polynomial time. N to the 100, it's also polynomial time. So as long as it runs in roughly like a polynomial in n amount of time steps, then it's polynomial time. And a polynomial time reduction is a reduction which it's like a function, and it maps instances of one problem to another in polynomial time. All right. So some notes: our theory only applies to problems where the answer is true or false, where it's like accept or deny. And okay, when I refer to theory, I really mean like not just like in the next slide, which is where we introduce NP completeness and NP, but basically it's like problems where, you know, for example, is there a given number in an array? Okay, it's not like, you know, count the number of or something like that, you know, or, you know, search for, or actually no, search for can be, but like basically it's like existence. So, but does this exists? Things like that. So yeah, of course that's all addressed in complexity theory, but you know, we're not addressing that. And okay, reductions must preserve correctness. if you have two problems and you take an instance of one, and under your reduction it maps to like an instance of problem B, then basically if the instance of problem A was output true, then the instance in problem B must output true, and likewise if the instance in problem A outputs false, instance in problem B must also output false. Okay, so it preserves correctness. Okay, now some more background. NP completeness. A problem is NP if its solution can be checked by deterministic Turing machine in polynomial time. I'm not going to go over what a deterministic Turing machine is. That's too much background, but like you can just think of it like any normal machine, how you would think a machine is. Okay, a problem is NP complete if it is NP and all NP problems reduced to it, polynomial time reduced to it, and I've covered everything you needed to know to understand that definition. Significance, if a problem is NP complete, that means it can't be solved in polynomial time. Technically, it can be, but the point is, okay, there's this thing called P versus NP, and it's like this famous problem, and what it means is like, we're trying to figure out if there's a problem that's NP complete, but also is like, falls in P, meaning that it's polynomial time, solvable, right? And if there was such an NP complete problem that was efficiently solved in polynomial time, that would mean that you could take any NP problem and polynomial time reduce it to that NP complete problem, and then solve that NP complete problem in polynomial time. And since polynomials add to create a polynomial, you'd effectively solve every NP problem in polynomial time, making P is equal to NP. And that would be kind of crazy. The implications of that would all the crypto systems in the world would break down. Then like machines can just replace mathematicians, and like proofs would become much shorter, and like all these crazy things you can look at a textbook to see, but like, yeah, so we've been trying for so long to figure out if P is equal to NP. We haven't found if P is equal to NP or not. So if you do find an efficient algorithm to an NP complete problem, then you've just won like $1 million and done a bunch of crazy things because you proved that P is equal to NP. But like, unless you want to spend all that time, then, the point is like, you're probably not going to find it. And so, just don't waste your time trying to find an efficient algorithm if you prove a problem is NP complete. Okay, dist NP completeness, that's like more related to the subject of the actual paper. It's just the average case analog, and we're talking about average case complexity, and it's like to solve a problem on the average instance instead of like the worst case instance, which is NP completeness. And like basically it means like if you have a distribution, meaning like probabilities given to each instances of your problem, right? It's like you find the weighted average of like the time steps, and you figure out like, that's your average case complexity. All right. So a distributional problem is just, as I mentioned, it's like a regular problem, and then it's also a distribution on your instances of that problem. Okay. And the distributional problem is dist NP if L is in NP. Okay, that makes sense. A distributional problem is dist NP complete, which is an analog to NP complete, if your distribution mu is natural. And I'm not going to go into natural, but it's like a polynomial sampleable. I'm not going to go into the definition of that though. And all dist NP problems, average case reduced to L. Dist NP case, average case reductions are a whole subject, and not a whole subject. They're like a whole, 2 pages of a textbook. I'm not going to go over like the background for that, but they're kind of similar to, they take the same effect as regular reductions. And so the whole definitions, all definitions are pretty similar to like the definitions for NP and NP completeness, but now it's like average case. All right. Okay, now my actual problem. Consider a permutation of size n, call it T, which is the text, and one of size K, call it the pattern P. And refer to T as our text, P as pattern. T contains P if and only if there's a subsequence of size K, subsequence of T of size K, S, and such that S has the same relative ordering as P. And that's the formal definition. I'm not going to go into the, all you need to know is that the ordering is the same. And okay, some examples. Text 136452, pattern 132. T contains P since 364 is the same order as 132. And like 3 is less than 6, 3 is less than 4, 6 is greater than 4. Just like 1 is less than 3, 1 less than 2, 3 is greater than 2. Another example, 1342, and pattern is equal to 123. T contains P since 134 corresponds to 123. they have the same relative ordering. So the problem PPM, pattern matching and permutations, is given a text and a pattern, determine if T contains P. And so earlier in like the 90s, it was proven that PPM is NP complete. And we can show a generalization of PPM. PMPP is NP complete also. That's what I did in my paper. It's not the main result. It's like, if you know what PMPP is, it's like poset permutations. Then the proof is not that important, but like whatever. Okay, and the main result though is that we prove that there's a distribution which paired with PPM forms a dist NP complete problem, which is pretty cool. And we use the following theorem. This is from a man named Noah Livne. Okay, he quit academia, which is kind of sad. But like, if a problem L is NP complete, then and if it's paddable monotonously and regularly, there exists a distribution that, when paired with it, will form a dist NP complete problem. And yeah, what it means to be paddable, that's explored in the we'll explore later. But like, yeah, so the whole game plan, like the whole strategy for the paper was like prove that the problem is paddable, and then use this theorem to show that like there's a distribution that paired with it will form a dist NP complete problem. And that's what I did for like the whole paper. We just prove that the problem is paddable. So now I'm going to go over some definitions. Regular paddable and monotonously paddable. I'm not going to, yeah, if you want to know more about this, just go into the paper, because explaining all of this takes, much more than 10 minutes. Okay, so just go into the paper if you want to see. Yeah, I'm going to go over the regular paddability proof. We take basically the whole regular paddability proof was like prove that you can pad a string of ones onto our problem instance, and like you can do this. I'm not going to show how, because that takes like too much time, but like basically you just take the first n natural numbers and you put it in front of your pattern and your text. And yeah, so example 1, 3, 4, 5, 2 and 1, 3, 3, 1, 3, 2. And if n is 4, you can put 1, 2, 3, 4 in front of both of them, and then like increment all your 1, 3, 4, 5, 2 and 1, 3, 2 to make like a valid permutation. Yeah, you increment all of them by like 4. And yeah, and then you can show that this satisfies all the requirements. That's like a whole page in like my paper. Too much time, but like, yeah. And monotonous padding, okay, that's like 2.5 pages. I'm not gonna go over that. Okay, but like, if you want to see all this, just check out my paper. It's pretty cool. Yeah. So okay, finally, conclusions. Further research. So I think that's what really this paper prompted, which is further research. Like for me, I don't know about the rest of the community, but like basically what I want to know now is like the flexibility of distributions. Which distributions arise from like my padding. If you pad in a different way, you can create different like distributions, and that's what I really want to know. I want to analyze Livne's original paper, which is like how what is the flexibility of distributions. And finally, acknowledgements. I'd like to thank my mentor, Jesse Stern. He was really helpful. And yeah, thank you. And I'll take questions at the end.
Thank you, Arjun. All right, we're going to move on to Ankhita for our last presentation.
Okay, let me share my screen.
Take your time.
Okay. Can you guys see that?
Hmm?
Okay. Hi, everyone. My name is Ankhita Sathanur. I go to Eastlake High School in Sammamish, Washington. My project is on the random forest identification of pulsars. So topics to cover are, first of all, what are pulsars and what are random forests? The data set I used, the having parameters I tuned, and finally the results of my study. So first of all, what are pulsars? They're really cool things in space, but from Earth, they just look like blinking stars. They're actually neutron stars, which are the leftover core when a really massive star dies. Some interesting characteristics about them are they're really dense, so they're only second to black holes, really. They also have a really rapid rotation and high magnetism. It's this combination of really rapid spinning and the high magnetism that creates the two beams of light you can see in the image here. And as the pulsar spins, these lights sweep across the Earth, causing the blinking that we see. Pulsars are really useful first in finding exoplanets, which cause noticeable disturbances in the regular spin rate of a pulsar. They're also useful in studying extreme states of matter. Since pulsars are really high density, the atoms and molecules inside of them arrange in really odd ways that you don't really see anywhere else. And finally, they're really useful in studying cosmic distances since they move through space while blinking a known number of times per second. Pulsar detection has typically been done through all-sky surveys and manual signal processing. This is just where telescopes are pointed at the sky. Over long periods of time, they look for light that flickers, and then humans visually process data collected from these telescopes. But as data collection has increased, artificial neural networks have been proposed to kind of go through the data faster and serve as first pass over data before humans process them. Some of the tools proposed are artificial neural networks. And these have varying degrees of success, ranging from around 85% to 98%. So random forests are a type of machine learning algorithm. They're a collection of independent decision trees that act as an ensemble. The trees are all trained on subsets of the training data, and then when the test data is fed, each tree makes its own individual prediction. And the prediction made by the most trees, they kind of vote, and the prediction that the most of the trees predict becomes the entire forest's prediction. The idea behind these is that a group of uncorrelated trees will outperform an individual tree as they're able to cancel out errors in individual trees. So really broadly, what I did in my study was create a random forest classifier to separate real pulsar signals from radio frequency interference and noise. The data set I used to create my model came from the UCI Machine Learning Repository and contained pulsar candidates from the Southern Hemisphere High Time Resolution Universe Survey, collected by the Parkes Multibeam Receiver in Australia. The data set contained almost 18,000 total data points, with 1,639 real pulsar examples and a little over 16,000 samples of radio frequency interference and noise. Features of the data I used were the mean, standard deviation, excess kurtosis, and skewness of the integrated pulse profile and ROC curve. The integrated pulse profile is the superposition of hundreds of thousands of individual pulsar pulses, those individual blinks. And when a pulse arrives on Earth, it arrives at different times across different frequencies due to the ionized interstellar medium it travels through before reaching Earth. And astronomers typically fit for the shape of this delay in the pulse profile, but there still remains an uncertainty, which is expressed through a DMSNR curve. After using that data set, I began building my model, and I evaluated my hyperparameters using two different metrics. The first is classification accuracy, which is the ratio of correct predictions to the total number of predictions made. The second one was an ROC curve, which plots the true positive rate against the false positive rate. So the first hyperparameter I tuned is called min samples leaf, which determines the minimum number of samples required to be at a leaf node, so those nodes at the base of a tree. But I thought there was an exponential negative correlation as this value was increased. The second hyperparameter was min samples samples that are needed to split an internal node of a tree, so one of the decision-making nodes kind of make up the body of the tree. There's no clear correlation found in min sample splits. This hyperparameter wasn't used in the final model. The next one tested was max leaf nodes, which sets the limit on the splitting of nodes to reduce the depth of the tree. So if its number continues increasing, the tree will just grow infinitely bigger. This one had kind of an interesting relationship. It was initially showing a positive correlation, which dropped really suddenly after 200. This probably occurred because the tree started overfitting to the training data and could no longer identify relationships in the test data. The next one's criteria. Criteria are really complicated mathematical equations used to determine the best split of a node. So and then splitting the data set into either the yes branch or the no branch, they want to maximize the amount of information they gain from that. So these two equations are ways to find values of that. So the three that were tested were Gini, entropy, and log loss, and Gini was the most accurate. The final hyperparameter tested was M estimators, which determines the number of trees that are in the random forest. It's kind of a pre-existing understanding that as you increase this, the forest will really only increase in accuracy. So we tested lots of different values for this, and we found that the accuracy kind of plateaus after 50. So here are kind of the results of my study. The final hyperparameters we used were M estimators is 50, min sample leaf is 1, max leaf nodes is 200, criterion is Gini. And the accuracy we got was 0.812, which kind of varied as the tree is rebuilt. And on the right here is the entire decision tree 0 of my random forest. And as you can see, it's really complicated and big. So we kind of zoomed into the top 7 nodes on the image to the left. And this really helps us look at what feature the node split on and at what value. And then if you look closely, you can see it kind of gives you the Gini value for that split. As part of the results of my study, we were able to identify relative feature importances. So in the graph, you can kind of see the 8 features we used to create the model, and then how important they were in differentiating between pulsars versus noise or radio frequency interference. Another interesting thing we found was that the model produces similar accuracy even with fewer features. So even when we removed the 3 least important features, the accuracy was still very high. And that really has implications for implications when not all of the features are collected or known, and so we could still be able to use this model on those. Some limitations of my study are it would not be useful in identifying millisecond pulsars. The model has not been trained to specifically identify those, so it wouldn't be very useful in finding those. Also, since all of the training data came from signals emitted by really normal, typical pulsars, it wouldn't be able to identify any unusual phenomena. And for that reason, human visual processing should still be involved at some level, so that hopefully we don't miss out on really cool discoveries. And then the final limitation was relating to the data set. Random forests work best in balanced data sets, while the one used was very much not. We had a lot more samples of interference and noise than real pulsar samples, which does reflect how rare pulsars are in space, but it does have implications for the accuracy of the model. So hopefully in the future, if this study could be redone with a more balanced data set, we would find more accurate results. In the future, hopefully this can be applied to future surveys. I've listed a couple of them here. They're all expected to produce a lot of signal data that wouldn't really be feasible to process through visually. So hopefully my model can be used as a first pass over the data collected by these, and then humans can go in and look at the samples that my model predicts as pulsars. So thank you, that's all I had, and I guess we'll start questions now. Thank you.
Sorry, thank you. We will start questions now. I'm going to go ahead, and if all of you guys want to turn your cameras back on, you're welcome to. Ankhita, while you're still pinned here, I want to ask you, what was the most interesting finding that you discovered as you were doing this research study?
Ranking the relative feature importances was really interesting, since we found that really the majority of the top features had to do with the integrated pulse profile. So we found that while the DMS in our curve was necessary and accuracy did drop when we didn't use that, it was not nearly as important as the integrated pulse profile, and that was very interesting.
Yeah, that's cool. Let me go ahead and unpin you and me. So I'm just going to go ahead and ask some questions to everyone, kind of go through this. If anybody has any questions, again, feel free to put them in the chat and I'll raise them to our presenters. And Siddharth, one of the questions that I asked was wondering as you were presenting is why quantum advantage? What was the reason that was the main thing you decided to focus on in your research?
So I chose to focus on quantum advantage because currently quantum advantage is one of the main, more public factors of quantum computing. So it's what's one of the main, newsworthy topics. But in reality, the main reason why I chose that topic was because quantum advantage is one of the main reasons why quantum computing is actually a viable solution in the future. Why do people want to use quantum computing? So without quantum advantage, it wouldn't be the drive for the field. So quantum advantage basically says, can quantum computers be better than or any current computational methods we have, either being faster or taking the same amount of time or using less resources? So in essence, the whole purpose of choosing quantum advantage is because is it possible to go further beyond the current limits of our computers? Is there anything more? And quantum computing is something very viable that I found out.
That's really well explained. I hadn't considered that before. You said that it might provide like solutions. What kind of solutions would it provide, or do you have any idea?
Yes, so one like problem set would be optimization related problems. So one example that I briefly hinted upon my paper was like maze solving. So more generally, optimization would be like trying to find like the best case scenario. So typically for quantum computing right now, one of which Fermi uses is in quantum chemistry. So for modeling molecules. So in this case, the quantum computer would work to like optimize like quickly model molecules compared to classical computers, so using less resources and so on. One more thing to note is that quantum computers are based on the same properties as actual molecules and other particles, compared to classical computers, which are based on like semiconductors, transistors, and electronics. So fundamentally, quantum computers work the same way as nature, making them inherently easier to model things that are hard for classical computers, like I previously mentioned, molecule modeling, drug development, and so on. So those are like some of the more like newsworthy things. As for optimization, that's more useful for like finance, like making predictions and so on.
Gotcha. That's cool that it can be applied to so many different areas. That's really neat. Varish, one question that I had after seeing your presentation was, well, first of all, it's really interesting that you decided to try to develop a product. Do you have any next steps for continuing testing this product or trying to share what you've discovered so far with other people?
Yes, so my first step would obviously be to like increase my accuracy of my code, because that's the most important. Because if like theoretically, if we want to put this in like a patient, like if we want to actually help like develop a final product, the accuracy would be the most important, because the whole point of this entire project is we only want to do like one surgery, and we don't need like multiple surgeries to constantly maintain this shunt. This shunt is like a one-time you install it, and then you're set for the rest of your life. It's supposed to maintain your cerebrospinal fluid levels. So again, accuracy is the most important. So I would focus all my research right now on getting the artificial neural network to be as accurate as possible. Next, obviously, I would try making this product more finalized. For example, the materials I'm using right now as my prototype is not like exactly sufficient enough to be like inserted in like a human brain. So like I'm gonna further my steps into like getting better materials, improving my accuracy, and yeah, and then after that I might create a final product which I can then try furthering my expansion of my, I don't know, yeah, something like that.
Sure, that's awesome that you're planning on continuing to work on this. Is there like, are you going to continue with your mentor, or is there another specific like path that you're going to choose to take?
Yeah, I'm planning to continue with my mentor because I think this project has a lot of potential.
Yeah, it definitely seems like if it works out, it could change lives. So that'd be really neat. Thank you. Arjun, we haven't talked yet. One question that I was asked for you is, it seems like you really went into a lot of mathematical models and spent a lot of time considering options as you dove into your project. What was the most challenging part of it for you as you did your research?
Oh, okay. The most challenging part was finding what to research, honestly.
Oh.
Yeah, because there's like so much has been done, so much, and then like a problem. So what ended up happening was originally it was like, I don't know, some slightly different version of the problem where it was like, you don't prove there is a distribution, you prove for like a given distribution, like I think it was the flat distribution. And then what ended up happening is if I did that, it would have been like a PhD level thesis topic basically. And then it was like, it was way too hard. And like, you know, but then the other alternative was I do a problem so easy that like an elementary schooler could do it, or not. Okay, that's too like, okay, whatever. But like you know, so that was like the real problem. It was like finding something that's just right. And I think I found something, you know, decent enough.
Sure, that happens all the time in research. Once you find that one big question you want to answer, you realize it's going to take years. It's not as simple as you think it was.
Mm-hmm.
For sure. If anybody else has any questions, I'm gonna give you guys a minute to go and add those, and if not, we'll go ahead and close out. Thank you all too for taking some time to share this information with us. It was really neat to learn so much about all the different things that you guys chose to pursue. Does not look like anybody's posting any questions in the Q&A, so I'm going to go ahead and close us out. Thank you again to all of our presenters, and I hope you guys enjoy the rest of the symposium. Have a nice day.
You too. Thank you. Bye.
You too. Bye-bye.
Thank you for the opportunity. Thank you.
Yeah, thank you guys.